Well, good morning, Calc 1 students. I hope this video finds you well. I hope that you had a wonderful Easter weekend. My family and I had a great time together celebrating all that Christ has done for us and ate some wonderful food. We did miss spending time with our extended family, but it was still just a great weekend, and I hope very much you had the same experience. Well, today I wanted to look at the notes from Chapter 4 that you will need for homework 21. And these are going to be coming a little bit out of section 4.1. We've already seen some information from 4.1. We're going to see a little bit more today, and then also section 4.5. So I want to show you a tool that is sometimes useful, not always. It's called the Extreme Value Theorem. And it's a nice result that somehow is intuitive, perhaps, but difficult to prove. We won't look at the proof at all. If f is continuous on a closed bounded interval, then f has an absolute max and an absolute min at some points on that closed bounded interval. And I encourage you to draw some pictures. Pause the video for a minute and sketch some pictures and see if you can find a counterexample. You won't, and hopefully in sketching some pictures you will understand what this is saying. And like I said, it really is very intuitively clear when you understand the statement, but the proof is a little bit more complicated. I wanted to make a couple of remarks. These extreme values that might happen more than one place. This theorem is not saying there's a unique point where the absolute max occurs. It's saying there's at least one point. There are some points where the absolute max and the absolute min occur. So for example, here's a function where the absolute max right here, this y value is the absolute max. It actually occurs 2 times. Here's a function where the absolute max occurs infinitely many times, and yet both of them do not violate the theorem. The theorem just says there's at least one place where there's the absolute max and there's an absolute min. So here the absolute min is 0, here and here. Here there's 1 absolute min, 2 absolute maxes, so on and so forth. All right, second thing. This statement does not say the only time you have an absolute min or max is when f is continuous on a closed bounded interval. It doesn't say that at all. It's easy to draw pictures of functions that are not continuous, that still have absolute maxes, or functions that are continuous on intervals that aren't closed and bounded where there's still absolute maxes. Let's just sketch a couple real quick in yellow. So here is a function that has an absolute max, and yet the interval, let's say, is let's say that it's going from 0 to infinity. Absolute max is clear. So you can have an extreme value in other situations, but please realize they're not guaranteed. You may not. So f might not have extreme values when f is not continuous or the interval is not closed and bounded. The extreme value theorem is guaranteeing you that you have an absolute max and an absolute min only when f is continuous and the interval is closed and bounded. It doesn't say you don't have them in the other cases. It just says you might not have them. So here's some pictures. Here's a function that's not continuous on a closed bounded interval, and you can see there's no absolute max. Here's a function that is continuous. My interval, though, is now open. It's bounded, but it's open. No absolute max. Here's a function that is continuous. Here's an unbounded open ray that goes out forever, and the function has no absolute max. It's getting infinitely close to this asymptote but never gets there. So just to be very clear, the extreme value theorem guarantees you an absolute min and an absolute max, i.e. extreme values, when the function is continuous on a closed bounded interval. You might have extreme values in other cases, but then again you might not. Okay, so question, how do we find the extreme values of a function? How do we go about locating where they occur? So there's really 2 main categories. One is if the extreme value theorem applies, as in your function is continuous and you're working over a closed bounded interval, then it's pretty easy. Then you know that extreme values must occur at local extrema or endpoints. So that gives us a really doable strategy. All we have to do is locate the critical points where the local extrema might be and then compare them with the endpoint. So we like that situation. You'll get some homework problems where you're working with the extreme value theorem, a continuous function on a closed bounded interval, and life is pretty good. What if it doesn't apply? If it doesn't apply, then we're going to use the first derivative, possibly the second derivative as well, depending, to see what's going on. So I'll show you examples of that further on, but I thought we'd start out with an example of using the extreme value theorem. So we'll stop this video here and then we'll